Hi everyone, and welcome to this recording for chapter 41. This is basically a follow-up on chapter 40. Chapter 40 basically dealt with the one-dimensional version of Schrodinger's equation. Of course, one-dimensional Schrodinger's equation which basically gives me the which is in a sense an energy equation, gives me the following expression. If you guys remember, it's minus h bar squared over 2m times the partial derivative of the wave function plus the potential in this case. And we took a simple case in here for the potential, namely the where a particle is basically contained in a box, okay, and is equal to E times psi. Of course, this is just a time-independent version of Schrodinger's equation, because we're assuming in here that the potential is independent of time, which will allow the separation of the differential equation, where we have the exponential in there for the time-dependent version of it. Anyway, so basically there is a term in here for the version with time that comes in from exponential negative I E t over h bar. Okay, so that is the by the way, h bar, if you guys remember, is the same thing as h divided by 2 pi. Okay, this term in here is actually the kinetic energy term. Remember, the kinetic energy term in this case boils down to this whole term. For it's the way that you would write it in one dimension is actually p squared over 2m plus the potential. In this case, this whole thing becomes what is known as the Hamiltonian operator times psi. This p squared in here was needed, this equation, just a reminder, was needed to satisfy the condition that the dispersion law for this wave, okay, is so that the angular frequency, or the frequency itself, f, is proportional to k squared, not to k. In the case of waves, the omega is equal to ck, or actually vk in general. The point being in here is that we need a k squared. That's why we actually worked out the equation in such a way to get a linear parameter with the time derivative versus that of the quadratic term in the second derivative with respect to space. That was for the case of the free particle. And then we said, okay, how about when there is a potential? Usually the potential in here is represented by the letter U, I'm sorry. When there is the potential, how are we going to handle this? Well, we said this looks like it's the kinetic energy is some basically an expression for the kinetic energy. So the total energy in the case of the free particle is simply the kinetic energy. So when there is potential, all we have to do is just add it. This was not really a proof for Schrodinger's equation, so that you know. But what we're saying in here is that the results from this equation were impeccable, and we used it in the case of tunneling, for example, for radioactivity and things like that from the problems we worked, and they work fine. Okay. However, real problems, especially if we're going to tackle the atoms in general and molecules later on, are not really one-dimensional problems. They are three-dimensional problems. So we really need to come with a version of the Schrodinger's equation that is going to help us in that case. So since this is a one-dimensional problem, I'm going to assume that this is the p the momentum in the x direction, for example. That's what we call the direction that we're dealing with. So in general, the momentum for a particle in 3D is just the x component plus y component plus the z component, of course under square root, because p is actually a vector in general. Okay, so how are we going to transcribe that? There is actually a different approach to quantum mechanics in this book, and actually in the introductory course of physics, to this subject, we usually introduce it in the historical context, and that's exactly what we're doing right now. We went from things that basically we were in classical mechanics. Niels Bohr model was actually a combination of an idea that did not make sense, and he himself was actually apologetic when the quantization came from actually Max Planck, was the one who was apologetic. All Niels Bohr did was basically borrowed that idea, which doesn't make sense in classical mechanics, and used classical mechanics, used F equals to ma actually, where A in this case was V squared over R, and he came up with a model of the hydrogen atom. where basically the hydrogen atom has those energy levels that to some extent explain the spectroscopic observations for spectroscopy when we do, for example, the analysis of the hydrogen atom, and it came with a very good result for it. So that was good in a sense that Niels Bohr's model. However, there was some problems with it. One of them, for example, Niels Bohr's model for the quantization that's from the previous chapter does not address the issue, for example, of other atoms other than the hydrogen atom. It works beautifully for the hydrogen atom, but there is no easy way for those stationary waves, stationary basically states for the hydrogen atom that Mr. Bohr basically came up with, that can account for the observed basically data for atoms other than the hydrogen atom. So there is a failure for his model pass hydrogen. Okay, so that was a problem. And of course we have a lot of elements. We have 91 other elements actually in the periodic table at that point that we need to account for. So that was a problem. The other problem also, and we're going to address this problem right now, is the issue that there was actually another issue that people noticed, is that the energy levels that Mr. Niels Bohr came up with were negative 13.6 basically electron volt divided by n squared. In the absence of a magnetic field, that's fine. I mean, we can explain the transition, basically the different spectral lines with the transition from one energy level to the other energy level. But when there is a magnetic field present, we will see that is that this energy level seems to be not really, the lines are not exactly as they are. Actually, there is a broadening of these lines, and when you look at them with the more precise basically devices, you will see that these lines, they split actually. So in the presence of a magnetic field, the spectral lines split. This is known as the ZMan effect. Obviously, Mr. Niels Bohr model has no way of explaining this thing. So that's what quantum mechanics came into play. We'll see also that there is a limitation for Schrodinger's equation as is without any modification to the fact that even there is a secondary, this is a so-called normal ZMan effect, but there is actually secondary ZMan effect known as irregular, let's put it this way, irregular ZMan effect. Okay, that is an odd one, and that is where basically the splitting of lines first of all happens on a finer level, and then the broadening of the lines even in the absence of the magnetic field. And so there is a problems in here that Mr. Bohr's model cannot address. So we really need to use, first of all, to see how we can improve using Schrodinger's equation, how we can improve on the hydrogen model basically that Mr. Bohr had came up with. So the first thing is this momentum. As I was saying before, is that there is actually a different formulation of quantum mechanics that follows some sort of, an algebraic approach, where there is a correspondence between a classical concepts like, for example, momentum and position versus quantum mechanical concepts, or operators as they are called in quantum mechanics. And there are several versions, basically several views, if you wish, to the operators and how you can view them in space representation. The position just transcribed as just a normal position, which is nice because then this potential, for example, retains its form. And the momentum, though, becomes the derivative operator with respect to the corresponding variables. So, for example, px as an operator, the component in the x direction for the momentum, becomes simply h bar over I, the partial derivative with respect to x. And the same thing with py, which is h bar over I, the partial derivative with respect to y, and pz with respect to z, basically. Okay, if you square this quantity, it's going to be basically negative h bar squared. Then the negative is coming from this I. When you square it, it's going to be negative. So h bar squared divided by the 2m, and that is the kinetic energy. Okay, so the kinetic energy is this entire term in this case. Okay, so this is the kinetic energy plus the potential energy, and now you have the whole system. So The equation that we have to really solve for any system is the following equation: minus h bar squared over 2m, the derivative with respect to x of the function, and I'm going to also assume that the wave function depends on only x, y, and z. So I already took care of the time dependence because I'm assuming that the potential in this case is not time dependent. I'm sorry, dy squared of psi of x, y, z. So we're taking generalization using what we learned already about the one-dimensional case. Okay, so this whole thing is multiplied by negative h bar squared plus the potential energy in this case, which may depend on all variables, times the function psi of x, y, and z, and this is equal to E times again the function psi of x and y and z. Okay, this is generalization of the one-dimensional time-independent Schrodinger's equation, where we included just the other parameters x and y and z. The operator del squared, which is really expressed in terms of these partial derivatives, is the Laplacian, of course. Okay. So you can actually symbolically write it as simply the operator minus h bar squared over 2m, this operator operating on x, y, and z, plus u psi is equal to E psi, where u, of course, in here is taken the potential that is dependent on the three variables x, y, and z, and so is psi, by the way. So this is actually Schrodinger's equation now in space, which should help us, of course, if we know what the potential is, which should help us basically to solve these problems, to solve to answer these questions related to the periodic table, not just a hydrogen atom. Okay, to be able to understand other atoms and also to address this ZMan effect that I was talking about in terms of the splitting of the spectral lines, and there is some sort of a hidden structure that Mr. Niels Bohr's model could not detect. Not all, I mean, for the hydrogen atom things work fine, with the exception, even in the case of the hydrogen atom, in this case the splitting happens in the presence of the magnetic field. Okay, so let's do a model in here. Let's take something like we did before, namely when we took a particle, that was supposed to be boxed in a well, okay, and that well had a width, I think we took it to be L, from 0 to L, and it was an infinite well in a sense that the particle cannot exist outside of that well. The particle is free to exist inside, that means there is no potential inside, and cannot exist anywhere outside. And for that we use the continuity equation of the function psi, because it has to be continuous function everywhere, because it's actually the second derivative in here, it's given in here, so its function must exist to have its wave function squared basically as the probability density for finding the particle or doing any measurements on it. And then second thing is its derivative must exist, so the function must be continuous everywhere. So we use the continuity equation at the boundaries and found that the energy is quantized, and we resolved that one. So let's do a similar problem, except now the particle is in a box. Free particle in a box. Okay, so I'm going to take a cube now. This is a very important example because we're going to illustrate a few ideas. One of them is the concept of degeneracy, and the other one is how the energy levels are actually computed, because this is a simple model that we can work with. So this particle is contained within this space basically, okay, of in the x direction, and in the y direction, and in the z. Oh, I'm sorry, did I put it backward? Probably. in the z direction, in the y direction and z direction. It doesn't matter. So this particle cannot exist anywhere outside because of the fact that the potential is infinite outside, but it's 0 inside. So u is 0 anywhere when x is less than or equal to L, and y is less than or equal to L, and z is less than or equal to L. Okay, so all of these are conditions. So that's the definition of what the box is in this case. Okay, and it's infinite outside. Otherwise, u goes to infinity outside. Okay, so the particle cannot exist outside because that's an impossible potential for it to have. No matter how much energy it has, it will never be able to get out of the box. So this is basically the problem of a particle inside a box. So let's try to see how we can solve the Schrodinger's equation. Obviously, Schrodinger's equation, when we sub the value of u in here, will be basically give me a psi that is equal to 0 outside, and a psi that is finite given by this differential equation with u being 0 inside. So this is the equation that we really have to solve. Minus h bar squared over 2m times the Laplacian of psi is equal to e psi, and this is in this space only. Outside, we know that psi is equal to 0. Okay? Particle cannot exist outside. So if I calculate probability in this case, psi squared integrated from basically anything outside is going to give me 0. That is the condition for it. So that means the continuity at the boundaries must be observed too, at x equal to 0 and x equal to L, and then also y equal to 0, y equal to L, and all of that. So the wave function need to vanish in those points. Okay. So let's do a trick that we did before, where we separated the variables, because remember, this is actually a partial derivative with respect to x, y, and z. So let's write this expression now as minus h bar squared over 2m. Again, the derivative of psi with respect to x plus, or minus, if you like, h bar squared over 2m, the partial derivative of y with respect to the partial derivative of psi with respect to y. Second one, and then another minus h bar squared over 2m, the partial derivative of psi with respect to z is equal to e psi. Okay, we're going to assume that psi of x and y and z is just the product of functions x of x, y of y, and z of z. Okay, and see if we can find a solution that basically meets these conditions. Obviously, the second derivative with respect to x is just the second derivative of x with respect to x, because these are constants as far as x is concerned. So all of these partials become straight derivatives. Furthermore, we're going to divide by the function psi. So there will be a yz in here, but when I divide by x times y times z, the y times z will cancel, and I will be just left with an x. Same thing in here, I will be left with a 1 over y, and so on and so forth. So this is what the result is going to look like. Minus h bar squared over 2m, 1 over x, the partial derivative, the regular derivative of x with respect to x, because x only is a function of a single variable x, minus h bar squared over, again, 2m divided by y, in this case, the partial derivative of y with respect to y, and then minus, not partial, I'm sorry, straight derivative, h bar squared over 2m, again, 1 over z, the derivative of z with respect to z is equal to e, because I divided by psi, basically. Okay, I divided everywhere by psi. Look, term by term things have to make sense. This term only depends on x, and this term only depends on y, and this term depends only on z. Okay, and all of them, they must be a constant when we add them up. So this must not depend on y and z, yet it must depend if there is only a y and if there is another y and z in here. So the only way that this would work is that this whole thing is just a constant, and this is another constant, and this is another constant, so that the sum of these negative constants, when you add them up, it's going to be this the energy of the system. So what I'm going to call in here, I'm going to call minus h bar squared over 2m times 1 over x, second derivative of x with respect to x, is just simply a constant, which I'm going to call ex. Okay? So this is a constant. Okay? And the same thing for the other two variables. So basically minus h bar squared over 2m, 1 over the last one is z. I'm sorry, where is this squared from in here? Sorry about that. Derivative of z with respect to z is equal to ez. Again, this is also another constant. So there is another equation in here, I didn't try it. So basically what we end up with then is the energy of the system then, E, must be the sum of this three constants. Although the one I didn't try it before, I'm writing it now. So that's basically in a nutshell what we should find in here, that this is the expression that we need to solve for. So let's find these constants, because there are a bunch of them that we need to find. And they have to be, because this is independent of y and z, but it is dependent if this is not constant. So the only way for this one to work is that all of them are constants. So let's solve one of them and make that generalization for the other two, because they are identical. So the equation that we really are looking at is the equation of an oscillator, because if I multiply the first equation by x, this is what I'm going to looking at. I'm looking at the derivative with respect to x of x plus, I moved this to the other side if you're worried about what happened in here, okay? 2m over h bar squared times ex times x is equal to 0, okay? Is equal to 0. So the solution for this equation is that if we try the exponential of some number and then may require it to vanish at the boundaries, similar to the problem that we did. This is identical to the problem we did in chapter 40 actually. So the solution is going to be some constants in here that needs to satisfy the conditions that x of x at x equals to 0 is 0, and then x of x, big X of x, not x of x, big X of x at x equals to L also must be equal to 0. So the only condition, the only way this is satisfied, actually we will find that it's like the previous problem and waves on a string, is that it's going to be x of x is some constant, what I'm going to call Cx, times the sine of, and in this case, if I look at these numbers, it's going to be some integer, nx, times pi times x divided by L. Okay, let's test this one. For x equal to 0, obviously this is 0 no matter what. For x equals to L, I will have an n pi, and n pi is going to be an integer. So nx in this case is an integer that could be, it cannot be 0, because if it's 0 then the entire wave function is 0. So it has to be 1, 2, and 3, and so on and so forth. Okay. So any integer but 0, because if it's 0 then the wave function is going to vanish, and then we don't have a particle at all. And we have a particle in here, okay? So we have to find it somewhere. So that is why the wave function cannot be 0 inside. It's 0 already outside, okay? And the same way, if I treat the other two, I will find that y of x, the only way that this is satisfied is there is another constant. So this Cx is just a constant. And we're going to choose it so that it meets the normalization condition, that we have to find the particle somewhere inside the volume, basically, between inside the cube. Okay, so this is a constant. Times again the same thing, sine of ny, which is an integer similar to this guy, pi y over L, and finally z sub z. Oh, why is z of y in here? I'm sorry. Is equal to Cz, which is another constant, sine of, and z pi z over L. Okay, where Cx, Cy, and Cz are constants, and then furthermore nx and ny and nz are integers that are from 1, 2, 3, and so on and so forth. Okay, so this condition will be met, and then we don't have a problem in here, so we have a solution for our equation. Obviously this number in here is related to the energy in this case. If we impose this Ex and the Ey and the Ez are actually going to be if I take the derivative in here, one derivative, I'm going to pull out nx pi over L. The second derivative, I'm going, of course, the sine converges to a cosine. If I take the second derivative, it's going to be n squared pi squared over L squared, and that is going to be this entire term. Okay, so in other words, Ex times 2m divided by h bar squared must be nx squared pi squared divided by L squared. Okay. In other words, if I work out this algebra, the Ex, the energy component, or at least whatever that term is, it's a constant at this point. When we add all of them, that's when we're going to get the energy. So it's n squared pi squared times h bar squared divided by 2ml squared. Okay, and the same thing for Ey is going to be an integer n squared pi squared h bar squared divided by 2ml squared, and Ez is going to be basically nz squared times pi squared h bar squared divided by 2ml squared. Okay, now what we need actually from this problem is the energy of the system. The energy of the system is going to be E, which is nx squared plus ny squared plus nz squared times that term, times pi squared h bar squared divided by 2ml squared. So we have found the energy, and it is quantized, as you can clearly see, because those are integers, n, x, and ny, and nz, and they're all basically three different integers. So the energy depends on these integers. So we're going to write this energy as nx, ny, and z, where just those are just labels, not products or anything like that. So it depends on these numbers. Okay, so the lowest of them is, of course, when nx is equal to 1 and ny is equal to 1 and nz is equal to 1, which is 1 plus 1 plus 1, which is 3. So that is the lowest energy level that we have found for our system. So and then you're worried about that constant, so I'm going to multiply all three of them back again to restore my function psi of x, y, and z, which is simply the product of all of them. So I'm going to call it just a big constant. So constant c is just the product of the other three constants, cx, cy, and cz, and normally we take it constant, we take it real when we do the calculations. So basically it's just the product of these three numbers. So if I do that, that's going to be sine nx pi x over L sine ny pi y over L sine of nz pi z over L. Okay, so this is actually the wave function, the time independent version of it. And if I want to get the whole version, all I have to do is just multiply it by that exponential of negative I t divided by h bar. I think I wrote it somewhere in here, didn't I? Yeah, that's the same thing. Okay, so that's the first separation that we have in there, and that is actually going to be the full-fledged version of the Schrodinger's equation. Now we need to find the c. To find the c, basically this is what we're saying. To find the c, this is basically what we need to say in here. What we're saying is take psi and multiply it by psi, and take the modulus of this function, which is real in this case. Everything is real. The integral in the volume between basically the entire space in here, which is just the cube in this case of length L, and that is going to be this number has to be 1, because we know that the particle exists must be inside the cube. If we do this, then we're left just with this integration of from 0 to L, 0 to L, 0 to L, and each one of them will give me just a factor of a half. So I'll have a half in here, and a half in here, and a half in here, which gives me an eighth times c squared is equal to 1. I'm sorry, I have to put actually n pi x over I mean, I will have an L actually in the integration because there is a volume L cubed in this case in here that's going to be pulled up. Okay, so in other words, do your change of variable and do the calculation, and you're going to pull the exact value in here. So it has to do with the volume divided by 8 in this case, and that is going to be square. It's going to be c squared. Anyway, I'm going to leave the calculation. It's really not important in here. All we need is just to have a normalized value so that you know what the C is. But the point being in here is the energy. That is usually most of the problem where we are going to be discussing things, okay? And that is where we're going to learn a few things about this this quantum mechanics for when we are in more than in space, basically. Okay. So the energy again, I'm going to compute E11. This is the lowest energy level that we're going to have. And that is 1 squared plus 1 squared plus 1 squared. So it's going to be exactly 3 times pi squared h bar squared divided by 2 ml squared. So this is the lowest energy level. Okay? And that is only one level, one energy. And that corresponds only to the function where nx is 1, ny is 1, and nz is 1. So the wave function, now we can normalize that wave function because I wrote it in general here, but I really have to be careful in here. This function now depends on nx, ny, and nz. So when I normalize this one, it depends which one I am doing it. So because each one of them is a mode actually that I pulled, because each mode is dependent on this integers. Okay, let's find now the next energy level. So obviously the next energy level, since nx, ny, and nz can be anything from where did we put this one? Yeah, 1, 2, 3, and so on and so forth. So the next energy level, we can just basically think that, okay, if I take nx to be 2, and this one's 1 and 1, so it's going to be 2 squared, which is 4, plus 1 squared, plus 1 squared, that's going to be 6. So it's going to be twice as much this number. So E, and you can clearly see that E211 is the same thing as E121, because this is 1 squared plus again 2 squared, which is 4, plus 1 squared, which is 1, so it's going to be 6 also. So this is the same thing as E121, which is also the same thing as E112, because 1 squared plus 1 squared plus 2 squared is the same number, 6. So there are 3 ways of finding the same, 3 different wave functions. Each and every one of them is different than the first one. The first one was sine of 2 pi x over L times sine of pi x over y over L, sine of pi z over L. The 2 was here. The second wave function that corresponds to 1 to 1 is actually sine of pi x, sine of 2 pi y over L, sine of pi z over L. And the third one, which is E112, is actually different wave function altogether. Sine of pi x over L times sine of pi z y over L and times sine of 2 pi z over L. So there's 3 different wave functions that are described by the same energy level in this case, which is the same number, 6 times pi squared over, which is just twice this number, which is just 2 times E11. So this is twice the ground state, twice the lowest energy level. Okay, good. So let's find the next energy level. The next energy level, we have kind of options in here. Either we have 2, 2, 1, or 2, 1, 2, or 1, 2, 2. Again, we have 3 different wave functions for the same energy level. So this is basically level 1. This is level 2. So let's find the third energy level. E221, which is going to be the same thing as E212, which is going to be the same thing as E122, and that will be equal to, let's do a quick calculation in here. So we'll have 2 squared, which is 4, and 2 squared, which is 4, that's 8, plus 1, that's 9, and 9 is 3 times as much as this number. So it's going to be 3 times E11, 3E11, 1, basically 3. So it's going to be, so if I'm drawing these 3 energy levels, this is how they look like. This is the ground state, and I only have one of them. Twice as much, we're going to have the next energy level, and there are three wave functions corresponding to that one. So we call this one a degenerate energy level, because E211 is the same thing as E121, which is the same thing as E112. So that was the energy level, and it was twice as much. So this gap is 2 times. If I go another level in here that is the same gap, I'm looking at this energy level E221, which is the same thing as E212, which is the same thing as E122, and this is actually, so this is 2 times E ground. I'm going to call this one G. And this is 3 times EG. Okay? I'm probably writing it outside of the scope of the screen, but hopefully you guys got the idea. Okay, let's find the next energy level. And here we have a kind of an issue. Okay, let's see that. Either 311, that's an option, or 222. Let's see what we have in here. Did I miss 11 energy level already? 2, yeah, that's good. Okay, let's do the 311. E311. Okay, obviously that is going to have in it, and there are 3 of them, they're all the same, by the way, in this case too. It's going to have 9 squared plus 1 plus 1. I mean, 3 squared, that's 9, plus 1 squared plus 1 squared, that's 11. Actually, it's going to be 11 because the E311 was had a 3 in it too, so I have to divide that by 3 in order to find it equal to basically how much it's EG. I mean, you can do the algebra quickly in here, and you will find what I'm talking about in here. 1, 3, 1, and 1, 1, 3. So it's going to be 11 over 3 times E ground. Okay, because the ground has a 3 in it. Has a 3 in it, and this number actually has actually 11. So I need to multiply it by 3 and divide it by 3 to get it to correspond to that one. So the next energy level actually is not a full jump. It's not basically 4 times. It's slightly less than that. And it's also degenerate in a sense that it has 3 wave functions corresponding to it. Okay. The next one, is it going to be E321 or E3 or 22? So let's see which one corresponds. Let's do E22. E222, and this is only one level. This is only one way to do this thing in here. So this level is not degenerate. So I did not try it E33. So let's go into 4. I'm sorry, into 4 times, which is roughly here. So this level sits in here, just barely below, because 11 over 3 is just less. So this is E311, which is the same thing as E131, which is the same thing as E113, and this is actually 11 over 3 times that ground state. Okay, let's look at E222. Obviously, 2 squared, that's 4. 2 squared, that's 4, and 2 squared, that's 4. That's 12 actually. This is the one that is 4 EG, because 12 is 4 times 3. So this is actually E22. And this is actually single state by itself. My point being in here is the following. The concept of degeneracy, which is an important concept, degeneracy, meaning for the same energy level, you have different wave functions. They're completely different wave functions. The reason why they are, because it doesn't matter. I mean, they're completely different because the first one has a 2 in here, the second one has a 2 in here, and the third one has a 2 in here, and you look, and every one of them is different than the other one. So the the wave functions are not the same. Sine of 2 pi x over L times sine of pi y over z sine of pi z over L is not the same thing as sine of pi x over L times sine of 2 pi y over L sine of pi z over L. They are different wave functions. So the wave functions are different, but they have the same energy. Another point that I want to make from this discussion here is the following. That as you go up in the numbers in here, sometimes the energy levels, first of all, they start to change in here, and I did not go any more. I mean, if we go to 4, you will see that this calculation becomes a little bit tedious and long. But the point being in here is that there is a jump in here. Which energy level is going to be occupied, if in case, for example, we're talking about atoms and things like that, they follow the energy. So this is going to be the lowest energy level. So it's going to be occupied first, then this one, then this one, then the natural instinct in here would think that after we exhausted 211, 221, then we're going to go to 22. No, the system jumps actually in the next number, which is 3, and then goes back to 2. And this is important because when you look at the periodic table, and we're going to discuss this one, is the distribution of the atoms in here where the electrons need to be sitting is not necessarily following the way that you might think. First of all, you have the n equals to 1 level filled, S, and then the next level is going to be filled, which is for n equals to 2. In that case, you have S and P, and you fill both of them, and then you're going to go to the third energy level, which has S and P, and then D. Once you finish the S filled and you go to the P filled, you're not going to go to the D in 3. Actually, you're going to go to the 4S. You're going, because that sits below that one in terms of the energy, just like this configuration here. It sits below it. So you fill that one, and then you continue to the P's from before, and then you go to the D. So that depends on basically where the energy level is sitting in terms of where it needs to be. So this is basically, in a nutshell, the point from this discussion here. Obviously, this is not exactly the hydrogen atom still, but this is an important example that illustrates the idea in here that we need to explore. Okay. So let's talk about the hydrogen atom now, because it's important that we have to explore that. How long this one? It's 42 minutes. Okay, this is what I'm going to do now. Okay, I'm going to break this video into 2 components, or at least maybe 3, because it's a long discussion. The next topic is going to be the hydrogen atom using Schrodinger's equation, and what will happen in Schrodinger's equation is the following for the hydrogen atom. First of all, the potential for the hydrogen atom is just depends on 1 over r. Basically, the Coulomb potential in here is the charge interaction between the nucleus, which is positively charged, and the electron, which is negatively charged. So we get the electrical potential in here, which is simply the product of the 2 charges, one of them being negative, so it's negative E squared divided by 4 pi epsilon naught divided by the distance. So the potential now is radial. Since the potential is radial, actually it's not advantageous to us to continue using Cartesian coordinates this way. So that's not really good. So we really have to use polar coordinates, okay? R, theta, and phi. Okay? And since the potential energy in this case is radial, we will see. Oh, there is another point in here that I need to make before we go, and that is how to lift the degeneracy, how to fix the degeneracy, and that's important for that discussion too. So, and that is the. So we will have then in that case, instead of nx, ny, and z, we will have 3 numbers still, because it's a problem in the 3D. We will have a number n, which is a primary number, primary quantum number, and then we will have a number L, and we will have a number mz. And the reason why we have to have them this way is that when we try to separate the differential equation in that case, and we're not going to do it because it's going to be too tedious and too long to do it, okay, is that there is a radial component to it, and the radial component has that symmetry in it. And then there is the 2 angles, the azimuth and the other angle, I forgot even what it's called, the latitude and the longitude. So in this case, those two angles, they have to have, actually they don't have potential in that direction at all. So in this case, they satisfy the so-called Legendre differential equation, and Legendrian in that case must be equal to 0. Legendrian breaks down into two components, one for the phi angle and one for the theta angle, and it's a polynomials basically that arise from it of trigonometric functions. Those are the ones that give us wave functions that vanish at infinity, because we don't want we want the electron, if it's far away from the proton, to basically be under no influence of that proton. So in this case, the wave function need to vanish there. There is another solution to Legendre equations that actually give you exponential growth, which doesn't make sense in physics. So in this case, the decay is the one that is acceptable, and those are the so-called Legendre functions, and they give us quantization in that case when we require that the function first of all is unique, and it has to be unique if I'm going to expect to have an expected value for its integral. So it has to be a function in this case when I'm doing the same calculation for the hydrogen atom. So the function has to be unique, and that gives me condition on phi itself, in a sense the quantum number mz in that case, and then I will also get another condition because the polynomials need to be finite at infinity far away from it, so that they don't grow indefinitely. And again, that gives me condition on L, and at the end both of them, they will add up to give me the condition of N, because again, and the probability of finding a particle outside of very far away from the nucleus is going to be 0. So that's going to give me a condition on N, and now I have 3 quantum numbers. Those are the ones that are going to be helpful for me to understand, first of all, the ZMan effects that I was talking about on them, and at least the first kind. The second kind is going to require another quantum number that cannot be included in this theory, and that is the spin of the electron. Okay. So anyway, so this is in a nutshell where we're headed. Okay, so I mentioned something about the degeneracy and how to lift it. This problem has energy that seems to be symmetrical in this case, and because of the symmetry I have the degeneracy. Let me assume for a second that the cube is actually not of all equal sizes. So I'm going to take a size, doesn't matter which, okay, doesn't matter. So I'm going to take the LX direction, for example, and make that one different than the other. So this is L prime actually, not like the others. So obviously the solution now will have in it the same stuff, except when it comes to the energy conditions in here, this will have an L prime in it. Okay. And the energy level in here will have an L prime in it. The other two will have an L. Okay. So I cannot really take L squared in here from this expression, so I'm going to remove it. I'm going to remove it in here. And I'm going to include it back into the expression when we have that included. So it's going to be L prime squared, and it's here going to be L squared, and in here it's going to be L squared. Now when I was counting the energy levels earlier, it depends where I put the 2, for example, where I this one in here. Let's do that. Okay. This one, if the 2 is here, which is fine for the wave function, we don't have problem with it. This will be 2 squared, which is 4 over L prime squared, plus in this case 1 squared over L squared plus 1 squared over L squared. This energy level is different than the other two, because the other one will have a 2 squared over L squared, and here we'll have 1 over L squared, which is the same as this one, which is 1 squared over L squared, or 2 over L squared. That sum is the same. However, here is going to be missed, so there will be a different energy level, different than this 2 in that case. In a sense, the ET211 will be an energy level by itself, and E12 and E112 will be the same energy level. So because there is an asymmetry in this case between the directions, namely the x direction is not the same as the other two directions, then in this case I broke the symmetry in the problem, and in the sense in this case as the degeneracy left. As a matter of fact, I'm going to start to break. As a matter of fact, if all the length are different, completely different, namely the x direction is different than the one in the y direction, different than the y, I'm keep on calling them backward. The x direction is different than the y direction, different than the z direction. Then in this case, what happened in this case is that hey, none of this will have, I mean, if I go back into my calculations again and sub the correct values in here and sub them in here, this will be a different number than this one. So every time I change these numbers, the energy levels are completely different than one another, and each and every one of them will correspond to its own wave function. And that is, now there is no degeneracy. Every energy level has its own one wave function. End of the story, period. And in that case, this is in a sense similar to the ZMan effect. Okay, so the ZMan effect is similar in the sense that in the absence of the magnetic field, we are back into a Niels Bohr model. Basically, we don't have a problem with that. At least the hydrogen atom. The hydrogen atom behaves exactly like Mr. Niels Bohr proposed. However, because then the energy levels for L and M, they are actually MZ, they are actually included, because the entire expression there also depends on n squared. So there is no problem. But the minute I put the hydrogen atom inside the magnetic field, what happened in that situation is there is a preferred direction for the angular momentum, because it wants to line up itself with the magnetic field. So now the degeneracy is broken, and in that case I will see the splitting of the lines. So that is basically in a nutshell an explanation, and it's actually the right explanation for this one in here, and that is what happened to the degeneracy of the hydrogen atom under the Schrodinger's equation, and in a sense I will have that ZMan effect 100% explained. Okay. The only problem is I cannot really explain the irregular ZMan effect with the degeneracy, because that exists even in the absence of a magnetic field. Okay, so that is a zero field, actually, the splitting of the lines. So in that case, there is an intrinsic property, and that is due to Mr. Stern and Gerlach experiment that actually showed without a shadow of the doubt that the electrons that had their own angular momentum, basically, which is associated with the motion. They called it spin, or at least somebody else after them called it a spin. And it's like a spinning Earth, but that's the wrong model. Okay, don't take that into account. But that will fix this issue also, the irregular ZMan effect, or the anomalous ZMan effect. And then we will have a complete picture of the hydrogen atom, at least with the 4 numbers now, not just 3 that are coming from 3D, not just because of the N for radial, L for the angular momentum, and mz for the component of the angular momentum along a direction which we call z direction. And then now we have the spin s. So we have 4 numbers, actually 4 quantum numbers to describe the hydrogen atom, and we will see how we take that and generalize to the other atoms, basically, that are not necessarily the hydrogen atom, any atom in the periodic table, and then we'll describe the periodic table, how we can understand it in terms of this. Okay, so this is the plan. This is part 1. I'm hoping that the second part will be also, there will be another part, at least second part, to complete this chapter. Thank you.